Hello, everyone. Welcome to this presentation from Rakuten Group, where we'll share you about our adoption of TiDB for our loyalty program, Rakuten Points. OK, first, a quick introduction of the team that is present here. So we have Vicky joining us from Tokyo. She's not presenting. She's in the audience, so she can help with the answers to any questions later on. She's the senior manager of our loyalty products in Rakuten Group. I am Rohit. I am joined from Toronto here. I take care of the point program on the product side. I have been associated with Rakuten for almost 8 years now. Together with me, we have Alex, the engineering manager, and Tim, the engineering lead, joining us from Dalian. So the agenda for today's presentation would be, I'll be introducing a little bit about Rakuten, the point program, the point platform that supports the point program, and the challenges that we are facing and how and what we are looking for. Then I'll pass on to Alex and Tim to explain on the engineering side of how we went about in adopting TiDB. OK, so let's get started. So first, for many people who don't know about Rakuten, just a quick brief about that. So it was an e-commerce service launched in 1997 by 6 employees. And from there, we have now grown to more than providing 70 services across 30 countries with 1.8 global members. Prominently in US, we have majorly 3 services catering to the end users. We have Rakuten Rewards, our affiliate business. We have Rakuten Wiki, our OTT service platform service, and Rakuten Kobo, the ebook, audiobooks, e-readers. Now, with all this gambit of 70+ services, bringing them all together as an ecosystem offering for our users is our flagship program, loyalty program of Rakuten Points. Now and that loyalty point program has been now supported by our next generation point platform. It's a active new system, hybrid multi-DC microservice architecture that provides this loyalty program of Rakuten Points for all our Rakuten services and users worldwide. Let's now quickly go into Rakuten Points. So first, about the scale and the growth that we have seen in Rakuten Points in recent years. So from our launch in 2002 till early this year, we have achieved a 4 trillion cumulative point issued to our users. Early next year, we are on track to achieve 5 trillion. In 2023 alone, we issued 650 billion points. And these were processed by approximately 8 billion transaction requests. And our platform also handles not only those business transaction requests to issue those points, but also other reference API calls of around 50 billion on an yearly basis last year. Now, to support that big growth and loyalty, we have our point platform that supports this point program. So the functions, we have our core business functions of granting points, redeeming points, showing the point balance. But apart from those core business functions, and the point platform supports a lot of other engaging features to our users. Let's go a bit more there. That's where we are going to connect why we wanted to use TiDB. So in the past decade, the core functions doesn't change much. We just had to grant and redeem. But now our business team wants to provide more engaging features to our users. So in the last decade, we have some rank program that was introduced. We made some changes there. We wanted to show their users on how much points you have been acquiring till their lifetime. On 2016-17, we introduced that feature to engage the users. In 2019, we are now showing users on a monthly level what kind of point acquisition and redeeming they're doing. And recently, in 2022, we are showing them in a calendar view what is their current point activity on a day-to-day basis. Again, all of these features, the point is to engage and provide an entertaining and gamified experience for the users to connect to this program. So it's no longer, Rakuten Points is now no longer about just you get points, you use points, but more trying to provide that engaging functionality of providing them some entertainment, some gamification, and gamified experience so the users can connect and also share that experience with the other users in that region. So apart from those business features and requirements that we have, with this much volume, Rakuten is now the #1 point program in Japan, and because of that, it's now considered as a societal feature, as an infrastructure. And that infrastructure is so much inherently used by our users that they cannot afford any system downtime. Anything we do, they cannot just afford that our system can go down because they use points as money in how the thing has been used. We also, as our system, has to be able to process those massive transactions without any delay. We have some frequently batch processing that happens every morning that needs to be handled without any delay. In our massive high traffic sales events, which we have every quarter, we have many users come to our website in bulk, and we have to return and show them those balances quickly and accurately. No latencies can be introduced during those kind of sales events. So now, with those business requirements of business core functions, those engaging new features that has been requested by our business team on a regular basis, plus these infrastructure level requirements, our legacy system was already hitting a wall. We were not able to meet all those requirements with our legacy system. So that's where we had to, in 2020, we took a decision to come up with a completely brand new next generation platform to support this point program. Let's first go with our legacy system. It was a pretty simple. We were using a licensed DB, a single DC setup. Our applications were getting difficult to scale, both from a feature level as well as from a traffic and a volume level. It was tightly coupled with the DB schema that has been designed. So unless we changed those DB schemas, tables, and everything, it was getting difficult to scale. On the DB side itself, because of the massive data volume that was being increased, it was getting difficult to scale up. That DB being a proprietary DB and a licensed DB, it has a high running cost. And then with those DB requiring upgrades, also without any downtime, was getting difficult now. Any support for any issues on the DB, we had to rely on the vendor for their investigation and support, which was also an operational inefficiency that we had with this legacy system. So then, 2020, with our team, we came up with a new architecture from a monolithic to a microservice-based architecture. What we did, now we started looking at different features in a different way. OK, we have our business core functions. Those business core functions, we kept it on a different layer. For all the other features of where we are engaging the users, we kept it on a different layer. So core functionalities, which are providing real-time experience to the user, and we need more resiliency and high scalability, we have it on the top layer, and it's being supported by Cassandra. All those transactions that we process get streamed downstream to our aggregation system, that we call it. Here, we are providing different functionalities, which we'll introduce in the next slide. Here, the capability we needed in this layer was how to be able to query the same transaction data in different ways. We want to query it from a user level. We want to query it from the clients or the different Rakuten services that we have. Or at the same time, also that layer has to be scalable for those growing needs of both functionality as well as data size. So let me give you a full, because it will connect to the next part of the slides, some of the core functionalities that we provide in this aggregation feature. First is about the point history, where the users, we want to show to the users all the transactions he has been granted or redeemed in a specific time period. So the query perspective is different. We also want to show to the users the accumulation of points in a certain specific time range. Again, this leads to a different querying on our same transaction data. We want to calculate the different rank of a user depending on his usage of points, different, flexible queries. And then accounting, because point technically is money, so we have to settle those points across different Rakuten services. So the same transactional data, which is a user-based transaction data, has to be summarized also from a client perspective. So that requires another different way to query our data, the same data. So those different perspectives required to be supported by our aggregation system. So with this challenge, we asked our engineering team, OK, so now which kind of a DB solution that can provide us this flexibility of querying as well as flexibility of scale for future? That's where now I'll hand it over to Alex, our engineering manager, who will explain how TiDB was chosen.
Thanks, Rohit. I'm Alex, engineering manager from Rakuten. So as a quick self-introduction, I have been working in the backend development related area for 16 years, 5 years in Rakuten. But this is my first time to be here in United States, California. So really appreciate PinCap and my manager, Vicky. So thanks for having me here. And from here, I will briefly explain from more technical perspective what kind of consideration was made in over selecting TiDB. So to the aggregation service that Rohit just mentioned, one important question is what kind of requirement regarding its database. First of all, the data. Yeah. So since it is required to store all the related information for the historical data display and the aggregation of the user activity history, so its database, it needs to be able to handle super large volume of data. And based on the massive data, when displaying the history data and performing the aggregation in different dimensions, then the query and the filtering condition will become very important. In other words, those queries, they has to be able to run as the online real-time queries. Also, since our business and data size, they keep increasing year and year. So it is also very important that this kind of database, it needs to be easy to scale out. The effort and the cost to scaling out the database should be reasonable. And furthermore, because we are going to operate and maintain this database in the long term, so it's also very important that we should focus on the easy to learn and support as well. So this is a simplified architecture diagram of our entire platform. So you can see the left side is our core system, which is mainly responsible for our core functionalities, such as granting the points to the end users and redeeming the points, balance management service, and we're using Cassandra as the main database. And the right side is our aggregation system I was talking about. So it will mainly decide the user rank, accounting, history, and those things. And it also needs to provide the clients the latest user information as APIs. Then if we consider the requirement of this two system, other than those data capacity and performance I just talking about, another important thing is that the performance of our core system, it shouldn't be affected by any other like downstream services aggregation system here. And another thing is that to achieve the high availability, the core system, it shouldn't be affected to the any failure of other system as well. So finally, we decide to choose to another separated database and make a complete separation between the core system and other systems. Then initially, our team proposed two solutions. The first one is to use Cassandra plus Apache Spark. The other one is to use MySQL and sharding. So regarding Cassandra and Apache Spark, I think we've used this in some of our components, and we are very familiar with it and very strong, confident about it. But due to the characteristic of Cassandra and Apache Spark, it has to take time to load the data from Cassandra and perform the aggregation in Spark. Then it's not suitable for providing the clients the latest information as APIs. And other than this, there are also many restrictions regarding the Cassandra. For example, its transactional processing, indexes usage, and the ability of joining multiple tables, etc. And other than this, because this aggregation service, it needs to provide the history data display, for example, to the clients. Then when the display content expands, the requirement will keep changing. Then it requires our extra development cost. And regarding MySQL sharding, we believe it is a good choice because most of the developers are familiar with MySQL and the flexibility that bring in by using SQL to fetch the data. But there are still some concerns from our team, which is even by using MySQL plus sharding, but if we run this on the massive data, there still could be a performance degradation. And other than this, to achieve the high availability, we want and we think we have to construct our database on the multiple data centers or even the different regions, availability zones. Then if we do this with MySQL and sharding, I believe it is a relatively challenging task. So these are all the considerations that we made when we try to select the database. And when our team tried to address all the problems I just mentioned above, and we came across a solution called NewSQL, which is the main topic and the reason that we're here. So I think NewSQL is a kind of combination of the traditional RDBMS and the NoSQL. It has the characteristic of the traditional RDBMS, and also it can give us the availability and scalability of the NoSQL. So here it is from our requirement and use case business perspective, we listed up some of the comparisons between NewSQL, NoSQL, and RDBMS. As you can see from this diagram, NoSQL has the strengths same as the relational database, which is the ACID transaction, the flexibility of using SQL, and the index, those things. And also, it is very easy to be scaled out. We just simply put more nodes in the clusters, and that's it. And also, it has the resistance to node and disk failure because of its distributed model, similar as the NoSQL. So we believe this is an attractive solution. Even we conclude that we will try to use the NewSQL or maybe some POC, there still could be many competitors of the solution that of NewSQL. So this we also listed up some considering points from our use case and perspective. In terms of the scalability, I think all the NewSQL solution, they are capable of doing the horizontal scaling, but TiDB is a little bit different. Two of its important components can be do the scaling independently. The first is the TiKV node. So TiKV node, we can place it on a relatively high performance spec of the node, for example, the NVMe disk or RAID disk. Then this data cluster size, it can be decided accordingly. And another one is the TiDB of node. It also can be able to scale out and scale in independently. Then in our use case, we can decide, it's flexible for us to decide to scale out the TiDB cluster before some of our big event happening. For example, we got a quarterly supercell event every year. And then after the event finish, we can decide to scale it in later. And another thing is that TiDB, it is MySQL protocol compatible. So it's very easy for our development team to adapt to this new database. And also TiDB has a component called TiFlash, which can help transform the TiDB to a kind of HTAP type of database, which we can run queries as row-oriented as well as the column-oriented. And we believe this can also reduce our development cost a lot. Also, I think TiDB provides some other very useful things. For example, the dashboard can help us do the analysis of the slow queries, and it also provides some supportive tools like Prometheus and GraphNow, which can scrap the metrics and can help us easily set up our monitoring, alerting pipelines, those things. Yeah, and last but not least, I think receiving the strong support from ThinkCap is also a very important thing to us. Then now I will leave the stage to our engineering lead, Tim. He will briefly introduce some of our actual experience of doing the POC and the experience of using TiDB in our production environment.
Okay, thanks, Alex, for the introduce. So hello, everyone. This is Tim from Rakuten Group. And I have been in Rakuten Group for 5 years and working as the engineer lead as of now. And I have 12 years of experience on the backend development, and mainly focus on the microservice utilizing the distributed database like Cassandra and TiDB. And this is the my first time in US, in California, in San Francisco. And more important is this is my first time in HTAP Summit. And I think that is all the content from my talk today. Of course, this is a joke. So in the next part, I'd like to introduce some performance verification result of TiDB from our team. So first, this is a performance verification example for our point history API. And as a verification environment, we built a small TiDB cluster by placing 4 TiDB nodes, 4 TiKV nodes. And the verification context is below. We continually write 90 million records prepared in our call service Cassandra cluster and to TiDB through the batch processing every 10 minutes to simulate the high spec of the data synchronization from our call services. And in the case 1, we continually measure the time and the load required to write 3 million records. And in case 2, in addition to case 1, we performed a select query by using a load type tool called K6 from Grafana Lab. And also a reference API deployed on the Kubernetes as a simple version of our point API. And then we simulate this environment which close to actual application and verify the impact of writing 3 million records and calling the reference API with 5,000 QPS at the same time. Now here's the result, the metrics data and the test result for case 1 and case 2. In the upper left, you can see the CPU and the memory usage. And in the upper right is the QPS and durations. And in this test, we just use the simple insert and the query. We found this system can handle the, about 25,000 write per second. And after adding 5,000 read per second, there's only 10% drop on the maximum write throughput. And the average response of the reference API is about 17 milliseconds. So we were able to confirm this small cluster can handle the massive data and write at the same time. And this is the real result from our production environment for the case 1. Comparing to the verification environment, our production database has 2 or 3 times time of the scale of it. So we achieved a higher performance in both job runtime and the maximal write throughput. In the next test case, we try to verify the statistics API. So firstly, let me introduce what is the statistics API. So this API is the one is used in widely visible screen for our users. And as one example, in this screen, you can see the historical granted points for specific user. And in the right side, you can see the pie chart of the statistics data for this user as well. Previously, we have experienced the performance issue due to the hotspots from our legacy system. So to verify the performance of this statistics API, we create a test dataset with over 100 million records in the single table. We also create 5 simulated user group with different user pattern. from the highest activity user with the maximum 15,000 records to the lowest activity user with the maximum 500 records. And we applied 1,000 QPS to each group and reach a total of 5,000 QPS for the select query. And the below one is the test query example. We summed up the amount from the history table for selected user in the past 6 months. And this is the test result and metrics for this stats API. The upper left is the QPS for each user group. The right is the CPU and the memory usage. The below one is the duration. So as we can see, under a load of 5,000 QPS, the TiDB cluster operates stably. And the CPU and the memory usage is about 17%. We judged the traffic was being handled by full use of the TiDB nodes performance. And more important is the duration metrics. We can get the response from the database in 2 milliseconds for the 80th percentile, and 30 milliseconds for the 99th percentile, so which is a good result. And for this case, you may also find it's the TiDB columnar storage, TI flash, might be more suitable for this case. And we also have the same thought. So in our plan, we would like to evaluate the potential performance improvement it can offer us. And above is the verification result based on our POC I present today. So for these two new API, with a load of 5,000 QPS, the performance and the response time performed well. And in both cases, whether it is a historical data query or static aggregation data, the response beyond our expectation. So therefore, we choose TiDB as the database to build our new statics and historical query API. And I think that is the real order contact for my talk about the performance verification. And if you are interested how we use the TiDB, please feel free to contact us. We will state this after our session. And you can also contact us by the emails. It's all fun. And I think that's it all. Thank you again.